Hi, in this video I'll be taking some of the previous year problems from the chapter flow through pipes. So let's see this first problem. Water flows through a pipe having an inner radius of 10 mm. So this is now inner radius. Okay, generally we are given with diameter, but beware, this is inner radius of 10 mm, so diameter will be 0.02 meter or 20 mm. Okay, I like to work in SI units because that helps me solve the questions very easily and accurately. Okay, at the flow rate of 36 kilogram per hour. So mass flow rate is 36 kilogram per hour, which is equal to 36 by 3600 kilogram per second, which is equal to 0.01 kilogram per second. At 25 degrees Celsius, the viscosity of water at 25 degrees Celsius is 0.001 kilogram per meter second. So what is this? This is dynamic viscosity or kinematic viscosity? The units state that this is dynamic viscosity. Okay, the Reynolds number of the flow is, Reynolds number, you all know that it is equal to rho Vd by mu. Now from the data given, mu is given as 0.001 kilogram per meter second. We have been given with diameter also, so that is 0.02 meter, but we don't know rho and we don't know V. Can we find this rho into V from mass flow rate? Yes, m dot mass flow rate is equal to rho AV. We know the diameter, so that means we know area. So 0.01 upon area is pi by 4 d square. D square is 0.02 square is equal to rho V. Solve it, the value will be 31.8309. Put this value in Reynolds number, and that implies Reynolds number equal to 31.8309 into what is the diameter, that is 0.02 meter, upon 0.001, that is dynamic viscosity. So Reynolds number will be equal to 636.619. Pretty simple question. Next, for a fully developed flow of water in a pipe, fully developed flow of water in a pipe having diameter 10 centimeter, that is 0.1 meter, right here only the values in SI units. Velocity is also given as 0.1 meter per second, and the kinematic viscosity is 10 raised to the power minus 5 meter square second. So now the kinematic viscosity is given and the value is 10 raised to the power minus 5 meter square per second. The value of Darcy's friction factor is, okay, so for this, firstly we have to check that whether the flow is laminar or turbulent, because for laminar the Darcy's friction factor formula will be different, and for turbulent the Darcy's friction factor formula will be different. Okay, so now let's check whether the flow is laminar or turbulent. How can we check that? With the help of Reynolds number. Reynolds number is rho Vd by mu. Okay, now tell me, you have been given with kinematic viscosity, which is actually mu by rho, so that is Vd by nu. Okay, velocity is 0.1 meter per second, diameter is 0.1 meter, nu is 10 raised to the power minus 5 meter square per second. So Reynolds number is 1000. That implies the flow is laminar. Some books state that if the Reynolds number is less than 2000, then the flow is laminar. Some say that if the Reynolds number is less than 2300, then the flow is laminar. But you can be sure that the values in the question that will be given to you will not be near 2000, so that there is no confusion. Okay, so Reynolds number is 1000, that means the flow is definitely laminar. So for laminar flow, Darcy's friction factor F is equal to 64 by Re. So 64 by Re is 1000, that is 0.001 0.064 is the answer. Okay, next question. Water flows through a 10 mm diameter and a 250 meter long smooth pipe. 10 mm diameter, that means 0.01 meter diameter, and 250 meter long smooth pipe at an average velocity of 0.1 meter per second. Average velocity is 0.1 meter per second. The density and viscosity of water are given. So you have been given the density as 997 kilogram per meter cube. So use this value only, not 1000 kilogram per meter cube. And the viscosity of water are 8.55 into 10 raised to power minus 6. Actually this is 10 raised to power minus 4. It's an error. 8.5 into 10 raised to power minus 4 Newton second per meter square, that is Pascal second respectively. Assuming fully developed flow, the pressure drop in the pipe is, okay, so you have to find the pressure drop in the pipe. So what you have to do is, first of all, you have to check whether the flow is laminar or the flow is turbulent, because nothing has been given that the flow is laminar or turbulent. Same as previous question, the concept is same again. So how can we check whether the flow is laminar or turbulent? We can check it by Reynolds number. Okay, so Reynolds number is equal to rho Vd by mu. Rho is 997 kilogram per meter cube. Velocity is 0.1 meter per second. Take care of the units. Okay, into d. D is 0.01 meters upon dynamic viscosity, that is 8.55 into 10 raised to power minus 4 Pascal second. Okay, so this gives the Reynolds number, which is equal to 1166.081, that is comfortably below 2000 or 2300 or whatever, I mean whatever the value you take, because some books state that if the Reynolds number is less than 2000 then the flow is laminar. Some say that the Reynolds number is less than 2300 then the flow is laminar. So we can surely say that the flow is a laminar flow. Okay, now pressure drop in a pipe, okay, in a pipe for laminar flow, you must have derived this and you must have learned this formula, that it is equal to 32 mu VL by d square. Mu is the dynamic viscosity, V is average velocity, L is length of the pipe, and d is the diameter. Put the values. 32, do we know mu? Yes, that is 8.55 into 10 to the power minus 4. Average velocity is 0.1 meter per second. Length of the pipe is 250 meters upon d square, that is 0.01 square. Solve this, you will get the pressure drop in the pipe over this length will be 6840 Pascal. Before writing the answer here, check the units, okay, in which you have to fill the answer. So that is you have to fill the answer in Pascal. You have got the answer in Pascal, that is 6840. So answer will be 6840. Okay. Next question. A fluid of dynamic viscosity, again mu is given 2 into 10 raised to the power minus 5 kilogram per meter second, and density rho is equal to 1 kilogram per meter cube, flows with an average velocity of 1 meter per second through a long duct. This is average velocity. Now this is a long duct of rectangular cross section. Okay, it's not a pipe, it's a long duct of a rectangular cross section. Assuming laminar flow, so it has been now given that the flow is laminar, so there is no need to check Reynolds number. The laminar flow is given. The pressure drop in the fully developed region per meter of the length. Pressure drop in the fully developed region per meter of the length. The keywords of the duct is. So you see this type of these type of questions are again and again asked in the GATE paper. So this topic is actually very important from the GATE point of view. Every year you can encounter a question from this chapter. Okay, so let's solve this question. Laminar flow is given. So just in the previous question we know that pressure drop for laminar flow is equal to 32 mu VL by d square. Okay, I will take this L here, so it becomes delta P upon L. This is the term we have to find, the pressure drop per meter length, per unit length. So this becomes 32 mu V by d square. Now we know mu, great, we know V. What will be d? Because in the previous question it was diameter because pipe was given. Now this will be, this d here is equivalent diameter for rectangular duct, and you know that this is equal to 4 AC by P. AC is the cross section area of the duct and P is the perimeter of the rectangular duct. So that implies D here will be 4 into 25 into 15. The dimensions are given. Perimeter is twice of 25 plus 15, which is equal to 18.75 mm. But be careful, you have to put the values here in meter. Okay, so that will be 18.75 into 10 raised to minus 3 meter. This will be D. Let me write here DE so as not to make any confusion. For pipe this will be equal to its diameter. For rectangular duct this is equal to 4 AC by P. Okay, so now you have all the values. Put the values in this equation and get the answer. That will be delta P upon L is equal to 32 mu V by d E square, which is equal to 32 into 2 into 10 to the minus 5. Average velocity is 1 meter per second upon 18.75 square into 10 to the minus 6. So solve this. Answer will be 1.8204 Pascal per meter. Okay, now the units will be Pascal per meter. Okay, so again there was a question on this topic. Next question. Consider fully developed flow in a circular pipe with negligible entrance length effects. Great. Assuming the mass flow rate, density and friction factor to be constant. Very important line. Mass flow rate m dot, density rho and friction factor f, they are given to be constant. Now it says that if the length of the pipe is doubled and the diameter is halved, L becomes 2L, D becomes D by 2. Okay, the diameter is halved, the head loss due to friction will increase by a factor of the head loss due to friction. Okay, so tell me what head loss due to friction is. It is equal to FLV square by 2GD, and it is also equal to FLQ square by 12D raised to power 5. Okay, it is basically what we have done to get this formula. We have actually substituted this V from Q is equal to AV. Okay, so V is equal to Q by A is Q by pi by 4 D square. So we have put this value here and get this, and we have gotten this result. Actually this constant is 12.1, but approximately we take this constant as 12 into d raised to 5. Okay, so यार ये काटना पड़ेगा यार, गलत बोल गया, मैदा नहीं बोला, कट करना है कहाँ से देख ले भाई, 14:45 के आसपास चेक करना है, मज़ेदार नहीं बोला गया। ओके, दोबारा स्टार्ट करना है यही क्वेश्चन। The next question is, consider fully developed flow in a circular pipe with negligible entrance length effects, assuming the mass flow rate, density and friction factor to be constant. Okay, the keywords: mass flow rate is constant, density rho is constant, and friction factor is constant. This is given. If the length of the pipe is doubled and the diameter is halved, now L is 2L, L becomes 2L, and diameter is halved, the head loss due to friction will increase by a factor of. We know that the head loss due to friction is equal to FLV square by 2GD, and it is also equal to FLQ square by 12d raised per 5. So what is the formula that we can use? I mean, should we use this or should we use this formula to be more convenient? To solve this problem very easily. Which of the equations we should use? We should use this one. Why? Because here F is constant, nice, G is constant, 2 is constant, great, L is varying, D is varying, and velocity is a function of D. I mean, velocity will depend on D. How? Q is equal to AV, so Q by A is equal to V. So velocity will depend on D because area is equal to pi by 4 D square. Okay, and this equation is actually derived by putting the velocity equal to Q by pi by 4 D square in this equation. When you put V is equal to Q by pi by 4 D square in this first equation, you will get this equation only. The only difference will be this constant is actually 12.1. So approximately we take this constant as 12. So this equation is actually derived from this equation. However, this is useful for us because mass flow rate is given constant and density is also given constant. Mass flow rate is rho into Q, mass flow rate is constant, density is also constant, so Q will be constant. So ultimately HL is equal to FLQ square by 12d raised to power 5. It will be dependent on L and D only because this is constant, this is also constant, 12 is a constant obviously. So can I say HL is directly proportional to L and inversely proportional to d raised to power 5 from this equation? Okay, this is HL. So that implies H old, let K be any constant, is equal to KL upon d raised to power 5. What about H new? That will be K, L becomes 2L, and diameter is halved, so that is D by 2 raised to the power 5. Okay, that implies 2 raised to the power 6 KL by D raised to the power 5, which is H old. So H new is 2 raised to the power 6, H old, 2 raised to the power 6 is 64. So the head loss due to friction will increase by a factor of 64. Okay, so you see the questions are actually based on the simple concepts, and this topic is very important from the gate point of view. Thank you.